Today we will talk about resilient modulus of soil. So you might have seen in IRC payment design, that is IRC 37. So we use the resilient modulus as a basic design input for the payment structural thickness design. So basically the resilient modulus is being used for unbound materials and also the bituminous material what we use in the payments. Now what is a resilient modulus, right? So in the resilient modulus basically we will see how material is resilient. Resilient means how elastic it is. So how easily it can recover to its original shape when you deform and remove the applied load basically. So if you see this basically in this diagram, this is the stress what we apply on a soil sample. Now this soil sample is normally 100 mm in diameter, 200 mm in height, right? So we will apply different stresses in this basically. One is the vertical contact stress. Now this contact stress is applied so that the loading equipment is maintaining a positive contact or a constant contact with the soil specimen, and then we will apply a cyclic stress because in the payment we undergo we see dynamic loads, which is time varying loads. So we apply a cyclic stress, right, which is not a static load but a cyclic stress, and then we also apply this confining pressure. This confining pressure will simulate the field conditions. This is the payment field. So each point is confined by surrounding other material. So to simulate those, we apply these confining pressures, right? So and then we apply S cyclic, S contact, and S max is basically sum of S contact plus S cyclic, right? So for this we will refer the ASTO T307 guideline. So there they have given few particular stress sequence on which we will apply load. So the loading will be in the form of a Haversine loading. So if you see here basically, now this is the stress pulse. Of stress pulse we have a rest period of 0.9 seconds. So why rest period basically? This will indicate that in the road or in the payments the vehicles won't come continuously, right? They apply a load, again there is a small rest period, the next vehicle comes. To simulate that particular condition, so what we will do, we will apply a load, right, for 0.1 second and allow a rest period of 0.9 second. Again apply a load of 0.1 second, then allow a resting period of 0.9 second. So in this what happens, in this particular 0.9 second and 0.1 second, so we apply stress, right, constant stress, automatically the strain will increase, right, the material will deform vertically, so it will undergo strain. Now as you increase the load, at some point the strain will get maximum, and once you give a rest period, the strain starts recovering. So whatever strain it underwent, right, there will be slow recovery, right, because of this resilient characteristics. But that recovery won't be fully. So some amount of strain will remain unrecovered, right. So that is unrecovered strain will be noted in the data. So this unrecovered strain indicates that the material is not fully resilient. If it is fully resilient, it will come to zero strain. It's elastic material, but it's not a purely elastic material. It's kind of plastic or viscoelastic material where some amount of deformation or strain will be unrecovered. Again, we go apply next load. So this goes on increasing. So for a given stress level, if you keep applying this kind of particular loading configuration, this after let's say 100 cycles. After 100 cycles, right, the unrecovered strain and recovered strain, it is this particular portion becomes constant. So it usually slowly increases. After some time it becomes constant. Now at that point of time, you will normally stop the test for the particular stress level and determine what is the recovered strain for that particular for 100 cycles, right? We'll apply, let's say we take a let's say 27 kilopascal, right? For this particular stress, we'll apply 100 cycles, and then the last 5 cycles or the next additional you'll apply again 5 cycles. This 100 cycles, which are conditioning cycles. Conditioning. Then again apply 5 cycles. So there you measure data of recovered strain and unrecovered strain. Then what you will do, you will use this particular data in this thing to calculate the MR, or by using S cyclic divided by recovered strain. So it is not a total strain, it is recovered strain. If you see total strain, right, it will be equal to recovered plus unrecovered strain. But here we are using only the recovered strain, which indicates the resilient characteristics. So let's say if epsilon is too high, then what happens? MR will be low. If it is too low, MR will be high. So basically indicates how resilient or how elastic the soil is, so it can easily recover once it is deformed. This way we will characterize the soil, right, using this resilient modulus test. So we use this Astro T307 as standard practice to conduct the test. So they have given around 15 different stress sequence, because unlike other bound material, the unbound materials should be tested in different stress levels, right? And then we arrive at a particular MR value or resilient modulus value. So the Astro T307 recommends 15 stress cycles or stress sequence with different combinations of S cyclic, right, and S contact. So then we have a form equation to find the MR, from which will determine the final MR of the soil. And now this MR can be tested for different conditions. It can be, let's say, at OMC or less than OMC or more than OMC, or we take from soil directly and test its MR. So all these things can be done in this particular testing procedure.
First oil the mold, then fill the first layer. Actually we want to fill it in 5 layers with 25 blocks each. So this is our final sample. This is our sample. The height of the sample is 200 mm and the diameter is 100 mm. We have made this by heavy compaction, 5 layers, 25 blocks each. So we will test this and use this sample for testing the modulus of resilience level. Next step is to make ready the triaxial chamber. First we will keep a porous plate. Above that our soil sample that we have prepared just now. Above that one more porous plate, and above that another plate made of fiber, plastic fiber. Actually this plate has a groove above this, so through this groove we will apply the load. Then tighten the screws. Now attach the pipe so that we can apply the air pressure inside the chamber. Now our biaxial chamber is ready. Through here we will apply the air pressure. This is a LVDT. LVDT means linearly variable differential transducer. So when these moves up and down, this LVDT will note the readings, how much is moving up and how much is moving down. Actually this is connected to the PC with the software. We can obtain how much motion is there. So through this hammer, loading cell will apply the load here, and this loading cell will apply the cyclic loading, and accordingly this will vibrate, and this will note the reading, how much it is deforming, and we can afterwards we can get the readings, means delta readings through the software, and we know the L also, so that delta L by L we can get the resilient rate. That I will explain after the video. The calculations I will explain. So this is the triaxial chamber. Now arrange the triaxial shell such that this bore is exactly at the bottom of this loading arrangement. Like that you arrange the triaxial shell, and remaining part we will do on the software only. Our manual part is over now. This is the software for the test. Fatigue09. So first on the software. Let's go to online display menu. So we have connected LVDT3 and LVDT4. The readings are coming to be 0.0946 and 1.373. So just adjust such that is just 0 or just above 0. Then go to the settings menu. So the LVDT3 and 4 is connected. So this is the failure criteria. Once it has maximum reached 5 mm, the machine will automatically stop. And also the load cell connected is 100 kg, so select 100 kg here and click OK. Then specify file for acquisition, means where you want to save your data file. So set the location, my computer or desktop. I'm saving it at triaxial. Sequence 1. Okay, so your data will be saved here. Then go to the dynamic test. So this is where we will start the test. So our frequency is 1 Hz, means 1 second 1 cycle will come, and loading period is 0.01 second, means 0.01 second it will load, and remaining 0.009 second it will rest. Means actually this kind of cycle is known as hour sign loading. Okay, so here we can adjust the number of cycles, and automatically it will count the number of cycles here. So initially we have to go for start activation, then just type some values here so that it will come down. Once the piston touches the ball or the loading arrangement, we can see it here. This is the loading. Actually it's applying 2 kilograms of load now. 2 kilogram is the seating load, or we can say constant load. So 2 kg of constant load is applying. So if we want to apply 10 kilograms of load, 10 into 0.1 it's 1 kg. But we cannot apply 1 kg because the machine itself will apply a minimum of 2 kg. So 2 is already there. So next we can type the amount of load amplitude of triaxial or repeater load that we want to apply. Just type it here. So I'm just typing 10 and just click enter. So it has started. You can see the pattern of the loading from here. Then once everything is set, click on start acquiring data. So the cycle count will start from 0. Once 500 cycle has reached, it will automatically stop. This is our data. After 500 cycle, it will automatically saved at the desktop. Actually not at the desktop, we have given the location as desktop. So it will be saved here. Then just drag the file into an Excel sheet. So this is our output. So this is our cycle number, time, load, LVDT readings, and we have used these 2 LVDTs, so just delete the remaining 2, only 2 LVDTs we have used. So from this you can plot the load diagram. Insert. This is how your loading diagram looks like. So this is how our loading diagram looks like, and this is the deformation diagram as we just plotted. So this length, or this is our delta L, means change in length, and we know the height of our cylindrical specimen, it is 200. So this delta L by L give you the resilient strain or recoverable strain, and you know the stress or deviator stress applied is 93.06, and confining pressure applied is 103.4, means confining pressure is the air pressure that you have applied, and correspondingly we have to calculate the bulk stress. The equation to calculate bulk stress theta is 3 times theta 3, means 3 times confining pressure and deviator stress. So that is our bulk stress. Accordingly, we will find the recoverable strain by deviator stress. We will get the modulus of resilience value. And after that, we will plot a graph between bulk stress and resilient modulus, because the modulus resilience value of a particular material depends on the confining pressure and deviator stress. Actually, deviated stress is an external part with vehicular loading, equivalent to vehicular loading, but confining pressure is the pressure that comes from the sides. So it varies with depth. If it's at the top, confining pressure will be less. As it goes down, confining pressure will be higher. So we cannot say a constant value, particular value for MR value for a given soil sample. So for that we will develop an equation so that we can say if the confining pressure and is this much and the deviated stress is this much, our MR value is this much. So actually what we will do is we will do the test at different deviated stress and different confining pressure. Actually this deviated stress and confining pressure values are given by the ASTO code. So we will adjust these two values and accordingly we will find the MR values. And we will plot a graph between bulk stress and modulus of resilience value. So here we have 10 points. Then we will fit a power curve and find the equation. Y equal to 0.793 x raised to 0.227 is the equation of this plotted line. Here y is the resilient modulus and x stands for bulk stress. So we can say if the bulk stress is this much, the modulus of resilience value is this much. So our ultimate aim of this test is to find the relationship between bulk stress and resilient modulus.